as we have seen already, that if we have a time series that follows an AR1 model like this, the yt equals to an intercept plus a slope times the lagged value of y plus the residual term, then if beta 1 is equal to 1, then we have a stochastic trend, okay? And this is just the same as unit root, okay? So these words, stochastic trend and unit root, they are used interchangeably. And if this beta 1 is less than 1 in absolute value, then you have stationarity. Okay, and if you have a stochastic trend or the unit root, then you have a problem. And if you have stationarity, then you can go on with your analysis. And the null hypothesis here is that you have the problem. So if you reject, or if you run a hypothesis test on this slope and reject the null hypothesis of this being equal to 1, then you assume stationarity. Remember that this is a one-sided test, right? So the reason why we do not test for difference here is that you only test for this being less than 1 in absolute value, because if it's greater than 1, then you still have a problem, because then you still have the stochastic trend. So how can you test this slope? Well, it's actually more easy if you subtract the yt minus 1 from both sides, and then you get the difference, which is just a new variable you make in your data set, is equal to the intercept plus a slope on the lagged value of y plus the residual. So here you are basically regressing the difference in y on the lagged value of y. And the delta here is equal to beta 1 minus 1. So now the hypothesis test become that the delta is equal to 0 versus the delta is less than 0. So this is a simple hypothesis test that you can use by using the output from your regression analysis. And our t statistic is t stat equals delta hat divided by the standard error of the delta hat estimator. So, and this is something you get from the output in your regression. And this t statistic is called the Dickey-Fuller statistic, and we just use df stat for short. And remember that the Dickey-Fuller statistic should be computed using the homoscedastic standard errors. So you would not add the comma robust, for example, in stata when you do this regression. What's interesting with the result from the hypothesis test is that if we do not reject that delta, if we do not reject the null hypothesis of delta being equal to 0, then we know that we have a random walk, we have a unit root, which means that we have a random walk process, which means that we have a stochastic trend in our process. And actually by transforming the data into differences like this, as we did in order to run the hypothesis test, we actually found that the solution to the problem, if delta is actually equal to 0 and we have a problem in the process of yt, because then we can just continue with the difference, and the difference is now equal to the intercept, which is a constant, plus the error term, and the error term is actually stationary because the average value of the error term is 0, and the variance of the error term is constant across time. It does not increase with increased time, but it's constant. So if you have a unit root, then you continue with the differences in your analysis. And if you reject the null hypothesis and you adopt the delta less than 0, then ironically you can let's see, we can do this. If you keep the or fail to reject the null hypothesis, then you use the differences, and if you reject the null hypothesis, so you adopt the alternative hypothesis, then you continue with your original model, yt equals beta naught plus beta 1 times yt minus 1 plus ut. So this is really what you use if the beta 1 is below 1, because then you have this process where if yt is here and t is here, then if you start here, then you have this beta 1 less than 1 term, which drags the process back towards 0. But of course the beta naught is forming like this floor, and the error term is inducing some variation, but you do not have this explosive kind of process, but you have actually got a stationary process. I think we should actually take one, or just explain one example here, because here you have like this process with a drift. Okay, so you have this this beta term is the drift term, okay? And if we think a bit practically here, then we can have yt here and time here. And what if the yt is an exponential? Oops, it's moving here. So it's process. And this process is often like this. And then you of course have variation around this. So you would have maybe something like this, but it's clearly an exponential process if you look at a large enough time frame here. And this exponential process, it's like a stock price, is actually non-stationary, because it has this both the change of mean, and you have this increasing standard deviation, or increasing variance, or standard deviation, we can say. And because the standard deviation of a stock price increases with increasing stock price. So one solution to this is to transform the stock price into a, let's see, I need more space here, into a logarithmic transform of the stock price, the ln of yt. Okay, and what would this look like? This exponential process is now a linear process. So what you have here is that, well, of course you would have some variation around the process, this linear process, like this. But what you get from this is that the returns in the exponential process is just a difference in the logarithmic process. So around here you would have a stable standard deviation of yt. Okay, so this is the standard deviation of yt. And how can you use this? Well, you can use this because now you can take the difference, you can work with the differences, and this difference will capture the trend, and the trend is captured by the beta note, right? And the variation around this line here is captured by the error term. So this logarithmic transform enables you to take the difference of the logarithmic transform. So now you can use the model ln of yt minus ln of yt minus 1, and this is equal to the difference in ln yt, and this is equal to beta naught plus ut. So now you actually have a stationary process of the stock price, which means that this is just the return in yt. Okay, so, and just a word of caution, this logarithmic approximation, I have to say, of the returns only works if the returns are quite small, like 1% or less. And this will of course happen if you gather data on a daily basis or a shorter horizon basis. And but if you gather data on, for example, on a monthly basis, then you could just calculate the returns as the arithmetic returns, in which you have yt minus yt minus 1 divided by yt, and you just subtract 1. Or you already had subtracted 1 here. So yeah, so this is just the return in y if you have a lot of variation in your data. If you do not have a lot of variation in your data, then you can use this logarithmic approximation, no problem.